So chapter 2, we're going to switch gears and we're going to talk about molecular representations. Most of you guys have probably seen this a little bit in Gen Chem or 110 or 121, whichever classes you took. But we'll do a little bit of review. And the problem of the day is based off of most of the review for you guys. So most of you are familiar with the molecular formula. And the molecular formula for a compound is a really simple way of telling you what atoms it has. So normally we start with carbon, we have hydrogen, and then any non-carbon hydrogen atoms are listed after that. However, the molecular formula, in my opinion, is a pretty crummy descriptor, right? Doesn't tell us how things are connected at all. So it's very, very limited. So let's make a note on that. It's got no info on connectivity. Organic chemists really avoid using molecular formulas because of that. Let me dim the lights up front. It's a little hard to see.
Are we getting into chapter 2 now?
Yes, this is chapter 2. All right, so the molecular formula, we don't use it a lot. We occasionally see it, but it just tells you really basic info. We do see something called the condensed structure semi-regularly. And with the condensed structure, we get more info on connectivity. And oftentimes, you'll see it written like this. Oops, sorry. That should be CH3, 2, CHOH. And the condensed structure is really a way of describing a molecular structure as if you were typing it out. So it will all fit on one line, and you can type it out on your computer. What does it mean when I have CH3 bracket 2?
You have two methyl groups.
Yeah, two methyl groups coming off of it. So we tend to group similar functional groups together, especially if there's multiple substituents coming off that are the same. So for example, you might see CH3 bracket 2, that means two methyl groups hanging off. Or you could see CH3, CH2, close bracket 2, that could mean two ethyl groups coming off of the next atom. So this carbon in particular has two methyl groups coming off of it. What else is coming off of it? Hydrogen, and what else?
Oxygen.
And an oxygen. So we're just trying to simplify this. I don't like using this structure, but I teach it because you will see it in your textbook, and you'll see it on standardized exams. Oftentimes, students have come back and they said, man, I just took the MCAT, and they don't do zigzag formulas. They do condensed structures, and it took me forever to redraw everything. So I want you guys to know how to interpret these structures. Like I said, this groups similarities. Like we saw that methyl group, there's two of them. And it gives the connectivity. So this is a better way of doing things. The last one is called partially condensed. Oh no. Let me slide this over. I'm running out of room on the screen. There we go. And with this, we group similar functional groups. So for example, those methyl groups, we might show them out as independent methyl groups. And we'll have a hydrogen coming off here, and we'll have an OH coming off here. So we abbreviate functional groups. And I abbreviate functional groups FG. And this is a pretty clear way of showing connectivity in an unambiguous way. However, it takes a lot of time. You have to draw each individual atom. You have to show all the individual bonds. Chemists don't have time for that. So we speed things up a little bit by using something called the bond line structure. And there's a handful of rules that we use anytime we do bond line structures. Does anybody know the first one?
The single line's a single bond.
Single line's a single bond.
You don't have to draw as carbons or hydrogens.
Yes, we don't have to draw carbons and hydrogens. That's my favorite part of this because most of organic chemistry is carbons and hydrogens, right? And like you were saying, a single lines, single bond, 2 lines, double bond, 3 lines, triple bond. It saves a lot of time. So let's write out a basic list of rules. First one is all termini and vertices, meaning a kink in your zigzag or an end, are assumed to be carbon. Unless otherwise labeled. There we go. The next one is all CH bonds are assumed but not drawn. A lot of times people will ask me, does that mean that every hydrogen's not drawn? No, only the ones coming off of carbon. If you've got a hydrogen coming off of oxygen, you want to draw that in. Same thing with nitrogen, sulfur, anything like that, you want to include those hydrogens. The other one, which I'm going to put a big asterisk in front of, is lone pairs are assumed. However, we'll do an asterisk, and I'll say, don't do this. Draw them. Why is it really useful to have lone pairs drawn out? It can help you figure out the geometry, right? Whether or not it has a charge. It gives you a lot of information if you have lone pairs. Once you get into more advanced organic chemistry and you're used to knowing what looks right, what doesn't look right, you can leave them out for the time being. But let's draw them just so we can figure out formal charges and hybridization for right now. So let's take an example of a structure. Those are the main rules for at least how I do it. The book may have more.
The book just says always show formal charges.
Oh yeah, that's kind of my assumed rule. We would draw formal charges on all the structures we use. These are unique to a bond line structure though. So let's take some examples. This is a really common structure. This is acetone. Many of you use it to get nail polish off your nails or to clean metal furnishings around your house. Some people use it to clean lawnmowers. This is our bond line structure. How many carbons do we have? 3, right? So if we think about it, we've got a carbon right there. It's the end of a line. We've got a carbon right there because there's a kink in our zigzag. And then another carbon right here. How many hydrogens do we have? 6. Do we have a hydrogen coming off here? No, that would violate the octet rule. So we have assumed hydrogens off of any carbon where you can have a hydrogen. However, if it's got a complete octet, there can't be a hydrogen there. So let's draw this out in that partially condensed structure. Or let's just do a full Lewis dot structure, I guess. We've got hydrogens coming off of each of these carbons, but we don't have a hydrogen coming off of the central carbon. So it's really, really useful for saving time. You don't have to draw out everything. There's a couple tips I want to give you guys too for drawing Lewis or bond line structures. Number 1 is use approximate angles. This is my personal pet peeve. So for example, let's take a look at acetone. You could draw acetone like that. Once in a while, I get a student that draws acetone like that. That just looks kind of funny. We know that these angles right here should be about 120 degrees. Try to get pretty close to a zigzag. Don't have an angle that looks like it might be 270 degrees. That just looks weird. Looks like a acetone doing jumping jacks or something. This is not correct. Number 2 is use dashes and wedges to show 3D layout. If needed. If we look back up at this example of acetone, what shape will we have for that central carbon? Trigonal planar. So we don't have to include three-dimensional dashes and wedges when we're dealing with something that's planar. However, when we get to more complicated molecules, we probably do want to use dashes and wedges to show whether or not it's sticking out towards you or away from you. If it's planar, just draw it in plane with the page. Last one. Include formal charges. This is true for any structure you draw, whether it's bond line, partially condensed, condensed. We need to know the formal charges because that gives you a lot of information. So let's take a look at some examples of why formal charge is so important with bond line structures. Let's compare this compound to this compound, where the central carbon's got a positive charge on it. They look pretty similar. The only difference is that positive charge. There's a lot more going on, right? What's the hybridization for that central carbon for the one on the left? Ah, tricky. We have an assumed hydrogen, right? So even though I haven't drawn a forced substituent, it's there. So we have to factor that in. So we've got 4 bonded atoms around that central carbon. So this would actually be sp3. What about this carbon?
sp2.
Ah, sp2, because it must be missing a hydrogen in order to have that positive charge. So things change a lot. Let's draw it a little bit differently. We'll draw it down below. If we think about this one, we've got a central carbon. We've got a methyl group sticking up. We've got another methyl group that's also in plane. We've got a methyl group that could be shown sticking out. And then we've got this assumed hydrogen that's kind of pointing back into the board. So this is an assumed hydrogen. Right, so it's tetrahedral. We've got angles of about 109.5. Looks good. Let's do the same thing for the one on the right. This time we've got a carbon. We've got a methyl group sticking out that way. Got another methyl group kind of sticking out of the board. And our third methyl group sticking into the board. So we know that this is actually trigonal planar. I'm trying to draw it flat, like we're doing the side-on view a little bit. What orbital are we missing if it's trigonal planar? So remember, we said this is sp2. What orbital is left over if we're dealing with sp2? P orbital, right? So let's draw this p orbital in. This p orbital is empty, right? We don't have an assumed hydrogen anymore, but this p orbital is hanging out above and below the plane here. So just by changing that positive charge, we've changed everything about this molecule, and it's important to draw these out in a way that you understand. And if you're having a hard time with bond line, practice converting between bond line to Lewis dot structure and then back again. Sometimes that can be helpful. Yep?
Does it rehybridize when there's a hydrogen? Wouldn't it be sp3 when it has a hydrogen?
Yeah, so in this example, this is sp3.
Right.
This is tetrahedral.
So then when it loses that hydrogen, it goes back to sp2.
Yeah, if it loses that hydrogen, this becomes trigonal planar and sp2. If it were to gain a hydrogen back, so a hydride in particular, a hydrogen and 2 electrons, then it would go back to tetrahedral, which is a little weird to think about, but we'll cover that when we get into the reactivity of cations. All right. So that was number 3. Right, I had 1, 2, 3. Let's do 4. Number 4 was draw lone pairs. And the example I like from the book that shows this is one with nitrogen, where they have a compound where we have nitrogen drawn, but we don't include the lone pairs. So the question is, does that nitrogen have 1 lone pair or 2 lone pairs? If it has 2 lone pairs, what charge does it have? -1. So we would do negative up here. If we only had 1 lone pair, again, that changes everything about this molecule, and what does the charge become? Positive. So it's really important to draw those lone pairs to give you a good idea of that formal charge, which also tells you the geometry too. All right, let's do a little bit of practice. I'm going to give you guys a structure, and I want you guys to help me determine the zigzag structure or the bond line structure out of it. So for the first one, is it okay if I scroll up? Okay. Let's do this compound. We'll do bond line structure. Remember, you don't have to show hydrogens. How many people think they've got it? A few people? I'll give you guys another little bit. All right. I'll show you guys my pet peeve ones first. A lot of times people will say, all right, we've got a triple bond here, right? So I'll do that, 3 line. And then we need another carbon, so I'll do a carbon like that. Is this wrong, right? Kind of right, kind of wrong? Kind of right, kind of wrong. What's wrong with it?
It's not linear.
It's not linear, right? We know that this carbon is going to be SP. It should be 180 degrees. We said we want to use approximate angles. So when we do this, let's try to have our triple bond and then our carbon coming straight off of it. Remember that this red dot is a carbon because that's where the triple bond stops. We've got a carbon right there and we've got a carbon right there. So even though it's not a true bend in that zigzag, it's an assumed carbon right there. All right, let's do another one. This time I'll give you guys the condensed structure. We'll do H, C, 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 H. Looks kind of funny written out that way. You guys want a hint with this one? All right, let's take a look at this first carbon right there. We know it's bonded to that hydrogen and another carbon. So it's got steric number of 2, which means it's what hybridization? SP, which means that carbon-carbon bond's probably what?
Triple.
Probably a triple bond, right? So that can get you started. We know that first carbon-carbon bond's likely triple. Raise your hand if you think you got this one. A few people? So it is tricky. Let's slowly go through it. We know we've got a triple bond, right? So we'll do a triple bond. I'll fill in red dots for now just so we can identify our carbons. That's the first 2 carbons. And then we've got a bond to our next carbon, right? Is that going to be single, double, triple? Single, right? In order to follow the octet rule, this carbon can only have 4 bonds. So one's a triple bond on the one side, one's a single bond on the other. If we had a double bond, we would violate that octet rule. Okay, so now we've got this third carbon right there. And that third carbon's attached to the fourth carbon through what sort of bond? Another triple bond, right? So if we think about this, we've got all 4 of our carbons, which I can show with these red dots. Oftentimes what I see students do too is they start thinking about that hydrogen and they extend this line out a little bit. Is that correct? No, because that would imply that it's not a hydrogen coming off of that last carbon, but rather a CH3 group. So with triple bonds, try to keep your triple bonds all in line. If your center one sticks out a little bit, it can be confusing and it can imply that there's a CH3 group coming off. Does that make sense? All right, so with the problem of the day, a lot of it is just kind of doing problems like this, trying to figure out how many hydrogens are on there and then how to draw the bond line structure. If you guys have questions, feel free to let me know.